Here we're going to construct a diagram to summarize subduction zones. And first we're going to show a subduction zone that forms because two oceanic plates are colliding. So all that's happening under the sea. So we're going to draw the sea surface up on top. We're going to look down below the surface of the ocean, and we're going to show two oceanic plates. Let's draw one over here on the right, like that. And we'll show that one moving to the left with this arrow, and it's running into another oceanic plate, and this one's going to subduct. Okay, so plates are moving toward each other. Subduction zone is a type of convergent plate boundary. Again, the plates are slabs of lithosphere. Underneath the lithosphere there's a asthenosphere, so we can label that. There's also a asthenosphere kind of in this wedge here, underneath this overriding plate and above the plate that's being subducted, so we should label that as well. The oceanic lithosphere can subduct because it's pretty dense, and the sinking of that dense, cold slab of oceanic lithosphere, it actually pulls the sea floor down a little bit. So you see how there's this low area in here. That's a very deep part of the sea floor, fairly narrow. It runs all along the boundary between these two plates, all along the subduction zone, and that's called the oceanic and oceanic trench. It's not easy for a slab of rock, huge slab of rock like this oceanic plate, to move down into what's also a big mass of rock, the asthenosphere. So tremendous amount of stress builds up all along the boundary here that's down below the surface, all along the margin of that subducting oceanic slab. And the stress causes earthquakes to occur. So like on our divergent boundary diagram, these X's, they're supposed to represent earthquakes. And you can see that right along the plate boundary, the earthquakes originate really not all that far below the surface, so they're referred to as shallow earthquakes. But the earthquakes originate farther and farther below the surface, right? The surface is up here on the seafloor. Farther and farther below the surface as you go farther and farther inboard on this overriding plate. So get these deeper and deeper earthquakes, sort of kind of showing where that subducted slab of rock is underneath this overriding plate. So earthquake activity, very, very common at subduction zones. This oceanic rock, it's got a lot of water actually that's tied up in the minerals that make up the oceanic crust on top of that oceanic lithosphere that's subducting there. And when it's subducting, it's going into hotter and hotter regions, farther and farther below the surface, so the heating causes the water to be released from those minerals, and the water starts moving out of the oceanic rock into this asthenosphere down here below the overriding plate. In the igneous rock chapter, we'll go into more detail about how adding this water, having that water come into the asthenosphere, it helps promote partial melting. Partial melting of the asthenosphere that generates magma. And that magma is going to work its way up through the overriding plate. Some of it might make it all the way to the seafloor, and you start to have volcanic eruptions on the seafloor. And that rock just builds up through time. Builds up through time. Eventually it can build up enough that It builds up above sea level, and then you have a volcanic island there. It's supposed to be a volcanic island. You can probably draw a lot better than I can. You know, we're looking at this cross-section view, cutting vertically downward, but if we think about a map view, we're looking at things from up above. You're going to see these volcanic islands forming all along the margin of that overriding plate. So it forms a chain of volcanic islands, and that chain of volcanic islands adjacent to a subduction zone is known as a volcanic island arc. Examples are the islands of Japan, the Philippines, the Aleutian Islands around the Pacific Ocean margin, and also in the Indian Ocean there's Indonesia, a chain of volcanic islands that make up the Indonesian volcanic island arc. Okay, so we have the earthquakes, the volcanic activity, the oceanic trench that's formed as we have two oceanic plates colliding. So now let's kind of quick erase this, and we want to show what happens when an oceanic plate and a continent collide. So let's relabel this, and I'm just going to write it in. Now we're going to draw an ocean continent collision. And it's going to look pretty similar, except, well, let's make the continental plate over here on the right hand side, and that's going to be above sea level, right, the top of it. And continental plates are thicker than oceanic plates, so let's label this CP for continental plate. We'll have it moving to the left, and then there's ocean over here. Coast is over here, and we'll draw our oceanic plate, the oceanic plate, right? Whenever you have oceanic plate collide with a continental plate, it's always the oceanic plate that's going to subduct, because the continental lithosphere, not dense enough to sink down into the asthenosphere. So we got our oceanic plate moving to the left, these are colliding. Still have the asthenosphere down here below. Okay, now what we're going to say is pretty similar to what we said before. We have an oceanic trench. I'm just going to say OC trench along the plate boundary, marking the subduction zone. We have the oceanic lithosphere that's subducting and trying to work its way down into the asthenosphere. So a lot of earthquake activity, the same pattern with shallower earthquakes close to the plate boundary, deeper earthquakes farther inland now from the margin of this continent. So we've got the earthquakes. And we're still going to have the water driven out of the oceanic lithosphere due to the heating at depth, and that's going to help the asthenosphere partially melt, produce magmas. Now we can show that, you know, some of these magmas, as they work their way up through this thicker overriding continental plate, some of them aren't going to make it all the way to the surface. We're going to get big igneous rock bodies down in the crust. Some of it can make it to the surface, and we get volcanoes. So we're going to have a volcanic mountain range here along the margin of the continent. Instead of a chain of volcanic islands, it's land here. So that's called, it goes by several different names, but one is to call it a Continental Volcanic Arc. Okay, so not a volcanic island arc, but instead a continental volcanic arc. So I think that's a good way to practice. Again, practice going over this material about the plate boundaries by drawing the diagrams. Lots and lots of test questions come up that deal with the different things that you see and different processes that occur at the different types of plate boundaries. So it's a relatively quick way to practice. And ask questions in class if you have any.